Let's say you just finished a physics test. Kinematics. You look down at your calculator at the last number you got. 0.4518. Not a very interesting number. You're bored, so you start playing around. You type in 1 minus 1 over answer. You hit enter, and let's say you do it again to your new answer. And again, but this time you stop. It's 0.4518. Somehow, after doing this 3 times, you got back the same answer. It has a period of 3. You're moderately puzzled. You ask yourself, what if I used 2 instead of 1? So you type in 2 minus 2 over answer. You do it once, you do it twice, and you do it 3 times. It didn't work. You do it one more time. It's 0.4518. This time, it has a period of 4. Now, you hypothesize what will happen for 3. Naturally, a period of 5 will come next. Once, twice, 3 times, 4 times, 5 times, 6 times. The period is 6. Now you try 4 minus 4 over answer. Once, twice, 3 times, but this time the now familiar number 0.4518 never comes back around. But why did it work in the first place? And why was there a jump from period 4 to 6 to, well, infinity? We started with a function 1 minus 1 over x, and we applied it 3 times and got back the number x. Let's look at what's going on here. So if we take this expression and simplify it, we find that it actually equals x. More generally, we can replace all the 1's in this expression with k's and solve for k. What you'll find is that x is irrelevant to the solution, which is k equals 1. If you use a period of 4, you'll find that k equals 2. With a period of 6, k equals 3. These are the 3 solutions we've already explored, but there's more. Here are the first few. For a period of 5, we get that k equals 1 plus the golden ratio phi. For a period of 7, we get this number, and for a period of 8, we get 2 plus the square root of 2. For 9, we get this number, and for 10, we get 2 plus the golden ratio. We can look at these numbers on a number line and look for some patterns. Notice how we have a mix of integers, square roots, and other seemingly random real numbers. Perhaps you also notice that these numbers are bounded above by 4. While it is not immediately obvious, there is a particular sequence of numbers in terms of cosines that has all of these properties. Perhaps drawing a circle will help us figure out the connection. We can remove all but the first few points for clarity. And then we can draw a circle. Now, connect each number to the point on the circle above it, and then to the origin. If we look at the angle associated with each value kn, we see that it's actually 2 pi divided by n, 1/nth of a full rotation. For example, k8 forms an angle of 2 pi over 8. This means that we can write a general formula for our numbers kn, 2 plus 2 cosine of the angle, 2 pi over n. And in this case, you can calculate that that equals 2 plus square root of 2. Now remember, this number k8 represents the number that we have to substitute into this 8-layer fraction so that it simplifies all the way down to x. Perhaps we can draw some sort of connection between this angle, 1/8 of a full circle, and the period 8. One guess might be that k minus k over x is a rotation by 2 pi over n. You could imagine that we start with a certain number x, and then applying the function kn minus kn over x rotates it by an angle 2 pi over n. Then, when we do it again, we've rotated it a little bit more, each time adding a new layer to our fraction, until we've reached a complete circle, and our big nested fraction is equal to x. And I'll tell you right now, this isn't exactly correct, but it does hint at what's really going on here. But the question remains, why should the repetition occur in the first place? And why should cosines come up in this seemingly unrelated context involving only subtraction and division? In the next section, Justin will answer these questions by extending our thinking beyond the number line.
To see the full picture, we have to think of these transformations k minus k over x not as functions of the real line, but as rotations of a space called the hyperbolic plane. The hyperbolic plane, the geometry we're used to from high school, is done on a plane called the Euclidean plane, which you can represent by a flat sheet of paper. And this is the plane we're used to, where straight lines are straight, and triangles have angles that add up to 180 degrees. There are, however, geometries other than the normal Euclidean geometry that we're familiar with. If we consider not a flat piece of paper, but a surface with positive curvature, we'll get spherical geometry, where lines are great circles, such as the equator or lines of longitude. And if we consider a surface with negative curvature, we'll get hyperbolic geometry. That's the geometry we'll be working with today. When working with hyperbolic geometry, there's one problem we run into immediately. In order to see hyperbolic space as it really is, we will need 4 spatial dimensions. I don't know about you, but I can personally only see 3. So instead, we'll have to stretch the space to fit on a flat surface. And this is known as a projection. Remember that every projection will distort the space in one way or another. For example, when we draw a map of the Earth's surface, we're using projection to stretch this round surface onto a flat plane. And the most common way to do this is called a Mercator projection, which stretches the poles while keeping the parts near the equator relatively intact. The reason you don't usually notice this is that the majority of the land we care about is close to the equator. The degree to which the surface is really stretched becomes much clearer if we pretended one of the poles was at, say, New York. Notice how near the pole, distances are blown up wildly, and how streets that we think of as straight become curved. Now let's look at a projection of hyperbolic space. While the sphere has positive curvature, the hyperbolic plane has negative curvature. And so the projection for the hyperbolic plane we'll use is called the Poincaré half-plane model, where instead of a pole where distances are infinitely stretched, we have a horizon where distances are infinitely compressed. We'll assign this horizon to the real line, meaning the rest of the hyperbolic plane will be projected onto the upper half of the complex plane. Just like near the poles of the Mercator projection, the Poincaré projection bends hyperbolic lines into curves. In this case, hyperbolic lines become either semicircles with a diameter on the horizon, or straight vertical lines. You can check that given any 2 points in the upper half plane, there is exactly one hyperbolic line passing through those 2 points. If we think of Euclidean space as a flat piece of paper, then transformations of the Euclidean space represent all the ways we can move this piece of paper around. For example, we can translate it, we can rotate it, or we can flip it around. And any combination of these 3 also represents a transformation. If we had to flip the piece of paper, we say the transformation is orientation reversing. And if we don't have to flip the piece of paper, we say it's orientation preserving. Algebraically, if we label the Euclidean plane with complex numbers, then a general orientation preserving transformation is going to be of the following form. We take c, we multiply it by a rotation term e to the I theta, where theta is the real number between 0 and 2 pi. And then we add a translation term, w, where w is a complex number. This transformation will be a rotation when theta is non-zero, and a translation otherwise when theta is 0. Just like how we move the piece of paper around to represent transformations of the Euclidean plane, we can imagine some four-dimensional creature grabbing a hyperbolic plane and moving it around to generate transformations of the hyperbolic plane. When we use the Poincare projection, a general orientation preserving transformation is going to be of the form f of z equals az plus b divided by cz plus d, where a, b, c, and d are real numbers. So we take a complex number z in the upper half plane, and we send it to az plus b divided by cz plus d. For example, if c is 0 and d is 1, then the entire bottom half of the fraction is 1, and we are left with f of z equals az plus b, which is the Euclidean orientation preserving transformation of first scaling by a, then translating by b. As another example, if a is 0 and d is 0, then after removing those terms, we're left with f of z equals b divided by cz, which we can rewrite as a constant, b over c, times 1 over z. This is a new kind of transformation called an inversion. Think of it like a reflection over a circle, in this case a circle centered around the origin. So we know how to translate, and we know how to invert. How do we rotate in the hyperbolic plane? It turns out that the criteria for rotations is the following. After scaling the top and bottom of the fraction, so that AD minus BC is equal to 1, a hyperbolic transformation is a rotation if and only if a plus d squared is less than 4. In other words, the absolute value of a plus d cannot be greater than 2. And yes, this means that the inversion we just saw was in fact a rotation of the hyperbolic plane by an angle of 180 degrees. Those of you that have seen some linear algebra might be making some connections right now to the determinant and trace of a matrix, but that's a topic for another video. For now, let's accept this condition for rotation and finally return to our original transformation, which sends x to k minus k over x. We can combine both terms under a common denominator, then divide both top and bottom by root k to scale it so that AD minus BC is equal to 1. Then our condition for rotation, that a plus d squared is less than 4, becomes root k squared is less than 4. In other words, when k is between 0 and 4, our transformation k minus k over x is a rotation of the hyperbolic plane. This to me is an incredible example of how math is just so connected, how a problem that started with fractions could be best visualized by using a hyperbolic plane of all things. Now using this representation, we can solve the mystery of what k had to do with cosine. It's not as simple as in Euclidean geometry, but given a hyperbolic rotation, which sends z to az plus b over cz plus d, there is a formula for the angle of rotation theta, which I'll show on screen here. Applying this to our transformation k minus k over x, we find that it has an angle of rotation theta equals 2 arctan of square root 4 minus k divided by k. And it's exactly when k equals 2 plus 2 cosine 2 pi over n that this angle formula produces an angle of 2 pi over n, or 1/n of a full rotation. So there's our explanation. When k is 2 plus 2 cosine 2 pi over n, the transformation k minus k over x is 1/n of a rotation of the hyperbolic plane. And therefore, it will have period n.